this at the lunch because late boy won't come, no? It's a little thing is good. Anyway, if everything is very clear, no need to study, no? There must be some problems. All right, so let's continue. So anyway, so here, I mean A minus B. So only thing is this, he has written this minus sign for the natural numbers. No, sorry, integers. This minus sign, this one, since they are integers, he wrote A minus B. Maybe I am kind of little dizzy or something, I don't know. But I thought about this thing several times. Somehow I ran into a little small doubt, kind of on the fence. Anyway, so somehow, if we agree with him, we should, we all can think, we can ask this thing from the paper, late boy, if he comes at the lunch. If he cannot answer, we will say no lunch for you. Think about it anyway. Anyway, somehow he is proving, if we accept everything written, A dash minus B and A dash, A lone dash B and A minus B are the same, that's what he is saying. Because of this we can now discard. Can you see now he is saying we can discard it. But plus plus? Plus. Because of this we can now discard the long notation and we use family operation of subtraction. Think about it, because you must know we have to be crystal clear. Okay, as remarked. No, let's go here. I'm going to the book. Remarked before, we could not use subtraction immediately because it would be circular. We can now generalize lemma 2.3.3 and from the natural numbers to the integers. Integers have no zero divisors. Let A and B be integers such that A B equals 0, then either equals 0 or B equals 0 or both. I don't understand why he writes within parentheses or both. He doesn't have to write no. When you say A equals 0 or B equals 0, it includes. No, this is math O, no? This is math O. And even in A level, also, I mean, when you say A intersection B, no, A union B, here, O here, O here. So it happens to be that these things belongs to both sides, but we don't say. It is included in the package. Doesn't matter. Again, proofs are not difficult. Not difficult. Something happened? No. Angle, some angle. No. Did I do something here? What is happening? Over there I'm pressing some other places. Cancellation law, that's also similar proof. We don't have to worry about too much, but we need to, there are exercises, you need to go through them. The ordering of integers. What am I doing? I am pressing in somewhere else. Let n and m be integers. We say that n is greater than or equal to m. We write n greater than or equal to m or m less than or equal to n if and only if we have n equals n plus a for some natural number a. We say that n is strictly greater than m and write n greater than m or m less than n if and only if n greater than or equal to m and n less. We have seen similar thing before, no? Thus, for instance, 5 greater than minus 3, because 5 is equal to minus 3 plus 8, and 8 is a natural number, So therefore 5 greater than or equal to minus 3, that is correct. And since 5 is not equal to minus 3. Clearly this definition is consistent with the notion of order on the natural numbers, since we are using the same definition, same thing. Using the laws of algebra in proportion 4.1.6, it is not hard to show the following. ABC integers A greater than B if and only if A minus B is positive natural number, they are not difficult. Addition preserves order, you can add any positive number. You can multiply by any positive number, order remains the same. If you multiply by a negative number, order reverses, no? If you multiply by negative 1. And transitive part is also clear, you can prove them, no difficulty. The rationals, order, there are some, exactly one of the statement, they are matter of writing. But when you are going to do them, a whole bunch of writing comes. Any problem, I did not notice them. Here, this is the problem. I told you there is a problem, no? Here he says Pn is not true for all integers. That's false, that's wrong, no? Logically. Because while P0 is free, how can you say that? So anyway, you know what he means. So as you replace his statement by, but that it is not the case that Pn is true for all integers, then you can do the homework. That's a good thing over there, by the way. Show that the principle of induction does not apply directly to the integers. More precisely, give an example of a property Pn pertain to an integer n such that P0 is true and that Pn implies Pn plus plus 1 for all integers n, but that Pn is not true for, it is not done, but that it is not the case that Pn is true for all integers. Think of an example that's a good one. It's not difficult, but when you are looking for an example, if you have the example, it is easy. Till you find the example, it is very difficult. Do you understand this problem? In usual induction, P0 is true. If Pn is true, then Pn plus 1 is true. Then you conclude for all n it is true. Here he is saying P0 is true, Pn implies Pn plus 1. Does not imply that it is going to be true for all negative integers. So think of an example for that. That is a good exercise to think. I am not saying it is difficult, but it's good one. You get the problem, no? It's a good exercise. The rationale, so okay. So everything so far is true, but only question was that the thing I got a little bit bothered. I don't know. I will have to think again. Maybe we should ask this guy from Leadboard. What is his thing? Okay, the rationals. Now here he is defining rationals. They are after reals. After that. After defining rational, absolute value and exponentiation, reals, real numbers, he defining the next chapter. Okay, doesn't matter anything. So, yeah, here. Rationals. We have now constructed the integers with the operation of addition, subtraction, multiplication and order. Verified all the expected algebraic and order theoretic properties. Now we shall use a similar construction. Over there somehow he used this longer line. He use our previous knowledge about subtraction to define how to add, how to add these sort of numbers and how to multiply these sort of numbers, and eventually he proved that this one and this one are the same, although we are a little bit doubtful about one line, one equal sign. Just like the integers were constructed by subtracting two natural numbers, the rationals can be constructed by dividing two integers. So it's a clever thing somehow he has done. Though of course we have to make the usual caveat that denominator should be non-zero. So it goes without saying. Of course, just as two differences a minus b and c minus d can equal a plus d equals c plus b, we know from more advanced knowledge that two quotients a by b and c by d can be equal if and only if he says AD is equal to BC. Thus, in analogy with the integers, we create a new meaningless symbol. Over there he made it longer. Subtraction line. Here now we added one more double lines. It is, but you can see he's a very clever person. Yeah, coming up with this.
In computer science we use that.
Eh?
In computer science we use that sign.
Is that computer science people know a lot of logic, no? That's why I told you you should go to Carnegie Mellon. Very clever people. The rational number is an expression of the form a double lines b, where a and b are integers and b is non-zero, of course. A double line 0 is not considered to be a rational number. Two rational numbers are considered to be equal if and only if AD is equal to BC as expected. The set of rational numbers is denoted Q. It's nice the way he writes somehow. Thus, for instance, 3 double lines 4 is equal to 6 double lines 8 is equal to negative 3 double lines negative 4. Now you need to understand is we don't know the meaning of double lines. But what he is doing is he is embedding the properties of actual with single line thing to double line, other things. Finally he is proving okay they are the same. That's what he is doing. This is a valid definition of equality. There is an exercise you can do it. It's not difficult. Now we need the notion of addition, multiplication and negation. Again we will take advantage of our pre-existing knowledge which tells us that A over B plus C over D should be equal to AD plus BC divided by BD, and that A over B times C over D should be equal AC divided by BD, while minus A over B equals minus A over B. Motivated by this foreknowledge, we define, motivated by that, he is defining A over B plus C over D must be equal to that. No? So that's why this is his definition. So that he is defining what to expect. That's what is their product. Again, same way, negation, the same way. But then we have to show that they are well defined bunch of things to do. Note that if B and D are non-zero, then BD is non-zero. By proposition 4.1.8, show the sum or product of two rational numbers remains a rational number. Anyway, 4.2.3, the sum, product and negation operations on rational numbers are well defined in the sense that if one replaces A double lines B with another rational number A dash double line B dash which is equal to A by B, then the output of the above operations remains unchanged, and similarly for C by D, that's what he has been doing. Again, this is, let's read one proof to make sure, because we have been so far playing with A minus B, long minus. Now we have double lines division. We just verified for addition. We leave the remaining claims to exercise 4.2.2 mechanical. Suppose A double lines B is equal to A dash double line B dash, so that B and B dash are non-zero, and A B dash equals to A dash B. We now show that A double line B plus C double line D is equal to, you replace A double line B by A dash double line B dash, since they are same. Now we have to prove that he says, we now show that they are the same. By definition, the left hand side is AD plus BC over, not over, no double lines. AD plus BC over BC. Again I say over double line BD, and the right hand side is A dash D plus B dash C over B dash, no, double line B dash D. So we have to show that these two are same, which expands, you multiply by, this side BD, other side B dash D, you get this thing. This is again AB dash equal to AB dash. You can cancel from cancellation laws or whatever. Now we have done all of them. So claim follows. Similarly, if one replaces C double line D by C dash over D dash, same thing you have to write, but you should do once. It is like there are many things you do once in life. We note that the rational numbers A double line 1 behave in a manner identical to the integers A. So A double line 1 plus B double line 1 is A plus B double line 1. A double line 1 plus B double line 1 is equal to AB double line 1 by definition. Minus A double line 1 is minus A double line 1. Also A double line 1 and B double line 1 are only equal when A and B are equal. Because of this, by definition, no, we are not saying in our own, it follows from the definition. Because of this, we will identify A with A double line 1. Over there we identified N with N long line 0. Here we are identifying A with A double line 1 for each integer A. So he is identifying here. We identified N with N minus 0 over there. Now he says N. He is identifying with A divided by 1. The above identities then guarantee that arithmetic of the integers is consistent with the arithmetic of rationals. Same thing. Thus, just as we embedded the natural numbers inside the integers, we embed the integers inside the rational numbers. We do the same thing like here. In particular, all natural numbers are rational numbers. For instance, 0 is equal to 0 double line 1 and 1 is equal to 1 double line 1. Observe that the rational number A double line B is equal to 0, 0 is 0 double line 1, if and only if A cross 1 is equal to B cross 0, that is the numerator, A is equal to 0. Thus, if and B are non-zero, then so is A double line B. So I mean they are just obvious. We now define a new operation on the rationals. Reciprocal. These are for rational numbers. If X is equal to A double line B is a non-zero rational, so that both A and B are non-zero, then we define the reciprocal X inverse of X to be the rational number. X inverse is the definition B by A, B double line B actually. It is easy to check that this operation is consistent with our notion of equality if two rational numbers A double line B and A dash double line B dash are equal, then their reciprocal are also equal. Then you have to take that A, B, A dash, B dash, all of them are non-zero, otherwise you can talk. In contrast, an operation such as numerator is not well defined. The rationals 3 double line 4 and 6 double line 8 are equal but have unequal numerators, so we have to be careful when referring to such terms. As the numerator of x. So he is saying when you have a rational number, you cannot talk the numerator of a rational number. We however leave the reciprocal of 0 undefined. Thanks. So here we define reciprocal also for a non-zero rational number. That's the only thing new. So follows of algebra for rational numbers x, y, z. These are mechanical. You can prove them actually, all of them. So it's not proving. What is important is you have to get the understanding how he is doing this thing. Because if we don't have the rational numbers, then he is defining rational numbers with the properties of the rational numbers we already know of. That's what he is doing. If x is non-zero, we also have xx inverse equals x inverse x is equal to 1. The above set of 10 identities have a name. They are asserting that the rationals Q form a field. You have heard? No? This is better than being a commutative ring because of the 10th identity. X inverse x, both are equal to 1. Note that this proposition supersedes propositions 4.1.6. I am sure this may be having more things than the proposition 4.16. Proof, I guess you can read it. I don't have to go through. No? This is mechanical. This is mechanical. We can now define the quotient x over y of two rational numbers as x and y, provided that y is non-zero, both by the formula. This is the definition. X is a rational number, y is a rational number. You know if y is a rational number, you know the reciprocal of y, what it is. Then x slash y is x multiplied y inverse. That's his definition. For instance, he says 3 double line 4 times 5 double line 6 is 3 double line 4 what? Divided by, I didn't notice. 3 double line 4 divided by 5 double line 6 is 3 double line 4 times, you take the reciprocal of 5 over 6, which is 6 over 5, then usual algebra. Using this formula, it is easy to see that a over b is equal to a by b for every integer a and for every non-zero integer b. Because his definition of x, this thing divided by y, is x cross y inverse. Using that you get this thing. Whether you have a one line b or a double line b, you get the same thing. Thus we can now discard the, here again he can discard this thing, not plus plus. The notation and use the more customary a over b instead of a double line b. In a similar spirit, we define subtraction on the rationals by the formula x minus y is x plus minus y, just as we did with the integers, place where we have a little doubt. Proposition 4.2.4 allows us to use all the normal rules of algebra. We will now proceed to do so without further comment. In the previous section, we organized the integers into positive, 0 and negative numbers. We now do the same for rationals. The rational number is said to be positive if and only if we have x is equal to a over b for some positive integers a and b. That is understood. it is said to be negative if and only we have x is equal to minus y for some positive rational number y. We know the positive one, then we know this one. And for some positive rational y is equal to x equals minus a over b for some positive integers a and b. Thus, for instance, every positive integer is positive rational number because every positive integer n can identify with n double line 1 or n single line 9. Double line, single line both are same. No? Thus, for instance, every positive integer is a positive rational number and every negative integer is a negative rational number. So our new definition is consistent with old one. Again, we have this trichotomy of rationals. Same thing. Let x be a rational number, then exactly one of the following three statements is true. X is equal to 0, x is a positive rational number, x is a negative rational number. Same thing, same proofs. Not much difference, but we have to be sort of consistent with their ordering of the rationals. Let x and y be rational numbers. We say that x greater than y if and only if x minus y is a positive rational number. Since we know the meaning of positive rational number, we know the meaning over there. And x less than y if and only if x minus y is a negative rational number. Again, we know that. We write x less than or equal to y if and only if either x greater than y or x is equal to y. And similarly, you know these things, but you need to do whatever the exercises. Basic properties of order on the rationals. Anything that I should make clear, I am just reading and going. Anything? Kuda? Yeah? No, they are not difficult. But you have to work. Order trichotomy. Exactly one of the statements, x equals y, x less than y. This is true for integers, natural numbers, then for integers, then for rational numbers. Finally for real numbers also. And proof is roughly the same. Order is antisymmetric, x less than y if and only y greater than x. Order is transitive, that is same proof actually. Addition preserves order, we had it before. And positive multiplication preserves order. And he doesn't have negative multiplication. Sometimes he writes, sometimes he does not. Doesn't matter any. We need to see that the above properties in proposition 4.2.9 combined with the field axioms in proposition 4.2.2 have a same name. They have said that the rational skew form an ordered field. Ordered field is another word in algebra. To the field you have these order axioms. That's all. It is important to keep in mind that proposition 4.2.9e only works when Z is positive. You know that, see exercise 4.2.6. Here in these exercises, nothing is. So, mechanical things, sometimes of course you have to provide the correct reasoning. Absolute value and exponentiation. We have already introduced the 5 minutes to 1, but let's go. No, because we took a little long break. We have already introduced the 4 basic arithmetic operations of addition, subtraction, multiplication and division on the rationals. We did that. Recall that subtraction and division came from the more primitive notion of the negation and reciprocal by the formula x minus y was x plus minus y and x over y was x times y inverse. And that's how we define the negation. We also have a notion of order and have organized the rationals into positive rationals, negative rationals and zero. In short, we have shown that the rational skew form an ordered field. Actually, real numbers is also an ordered field. So these names are redundant for us. We are trying to, actually what we are defining first in natural numbers, then integers, now rational numbers, and we are showing that according to the definitions, usual things are true. According to their definitions, what we know are true. That's what we are doing. One can use these basic operations to construct more operations. There are many such operations we can construct, but we shall just introduce two particularly useful ones, absolute value and exponentiation. For us, those who are interested in analysis, absolute value is very important for us. Analysis comes from absolute value. If x is a rational number, here he is defining only for rational numbers because we are building them. But absolute value is defined for any real number or even for any complex number. If x is a rational number, the absolute value, we write these two vertical lines and x in between. We call it modulus of x. I don't know how he reads. We can read that absolute value of x, by the way. Of x is defined as follows. If x is positive, then absolute value of x is x. If x is negative, absolute value of x is negative x. If x is 0, then absolute value of x is 0. That's definition is easy. Now we are coming to this analysis, important definition, which uses absolute value. Let x and y be rational numbers. Again, this is true for real numbers also. So far we don't know what real numbers are. That's why he is saying rational numbers. The quantity, absolute value of x minus y, is called the distance between x and y, and is sometimes denoted dx comma y. Dx comma y, distance between x and y. Thus, dxy is equal to absolute value of x minus y. That is the definition. That is very, very important for us after chapter 6. Every line we write, dxy is there, whether we like dxy or not. Every line, everything we talk about in analysis is dxy. So very important to get that understanding. Just by looking at the definition, you can see something. dxy and dyx both are same. Because absolute, by the definition of absolute value of x, absolute value of x and absolute value of negative x are the same. Absolute value of x and absolute value of negative x both are the same. So how can we prove? If x is 0, definitely easy, no? He says if x is 0, say case 1, x is 0, then negative x is negative 0 is also 0. Therefore, absolute value of x, therefore absolute value of 0. So in this case it is obvious. Case 2, let's take x greater than 0. Then absolute value of x is x. And if x greater than 0, then negative x less than 0. No? Therefore, absolute value of negative x, according to the definition, if the number is, if x is negative, absolute value of x is negative x. Since this number is negative, absolute value of negative is x is negative x. have you shown that negative is so anyway, for us, after chapter 6, assume now we are after chapter 6, negative is case 3. So far, anywhere we did not prove it, no?
Yeah, even when there was a minus b into c minus d,
Yeah.
even then he used minus e to minus x plus b.
Oh, yeah. Without telling us.
He just used to define.
He covered it by the definition. Then case 3, if x less than 0, then mod x is negative x for sure. Then negative x, if x less than 0, negative x greater than 0, therefore mod x is negative x. So, complete the proof. Assuming negative is somehow we should go carefully check with it. You know, you are right that he played the game by in the definition it was included. Let's see, somewhere he has to do it. Okay, anyway, so he says mod x greater than or equal to 0. Just by looking at the definition, you can say that. Also, mod x equals 0 if and only if x is equal to 0. Triangle inequality, mod x plus y less than or equal to mod x plus mod y. You should prove it carefully because we are in after chapter 6. Oh, this is everywhere, more than everywhere. We have the inequalities x what? Minus y less than or equal to x less than or equal to y if and only if mod x less than or equal to y. That's true. In particular, we have x lies between minus mod x and x. I call it, by the way, you maybe not understand, I call it modulus. X. Multiplicativity of absolute value. We have mod xy, absolute value of xy equals absolute x times absolute y. In particular, absolute value of minus x is equal to absolute value of x. Non-degeneracy of distance. Always there is a distance greater than or equal to 0. We are not going to not to have any distance. Also dxy equals 0 if and only if x is equal to y. Symmetry I told you before and it is obvious. But you should prove once. That's important because to me, I have wrote them 10 million times. Triangle inequality dx is z less than or equal to dxy plus dy is z. Very important. These are absolute value and dx thing in analysis all over. Now again he is doing something that nobody does. Absolute value is useful for measuring how close two numbers are. Let us make a somewhat artificial definition. Epsilon closeness. So this is not in other books, by the way. Somehow, let epsilon greater than 0 be a rational number, but this yx less than or equal to epsilon, this is analysis. Always analysis is about distance. Let epsilon greater than 0 be a rational number and let xy be rational numbers, because so far we know only about rational numbers. That's why he is talking for rational numbers, but otherwise for real numbers. We say that y is epsilon close to x if and only if we have dyx less than or equal to epsilon close to x. Y is epsilon close to x. He says here is x, here is y. Y is epsilon close to x means this length is less than epsilon. Less than or equal to epsilon. It doesn't matter. But anyway. this definition is not standard. He says that in mathematics textbooks we will use it as scaffolding to construct the more important notion of limits and consequences. Consequences are very important. That is analysis, limits, analysis. Analysis is nothing but limits and consequences. That's all, nothing else. Later on, and once we have those more advanced notions, we will discuss the notion of epsilon clause. So for, I guess it's a provisional thing for him. He is using epsilon clause. Example 4.3.6, I guess you can understand that. No, I mean, this matter of reading. Only thing is, x and y are epsilon clause means the distance from x to y is at the most epsilon. That's what it means. So these are you can understand, so I don't need to go through. Let x, y, z, w be rational numbers. If x is equal to y, then x is epsilon close to y for every epsilon greater than 0. That is very easy to prove. Conversely, though I say it is very easy to prove, you should do it because you are doing it for the first time. No? That is why. Conversely, if x is epsilon close to y for every epsilon greater than 0, then we have x is equal to y. I guess I gave you that as a problem in one of the homework sets. Eh?
Between every rational number and irrational number, there is an irrational number. You said that's
No,
what
it's
you-
not that one. No, I remember I gave that problem. No, I'm saying if x is epsilon close to y for every epsilon greater than 0, we have x is equal to I mean, I did not write that way, but my same meaning it boils down to. Let epsilon greater than 0. If x is epsilon close to y, then y is epsilon close to x, obvious. Let epsilon delta greater than 0. If x is close to y, epsilon close to y, and y is epsilon close to delta close to z, then x and z are epsilon plus delta close, follows from the definition. Let epsilon delta greater than 0. If x and y are epsilon close and z and w are delta close, then x plus z and y plus w are, they come from definition. We just do it. Remember, however, now we are almost getting to analysis epsilon, delta, dxy, absolute value, modulus. These are analysis. So I am happy. Otherwise, we are talking about that. We have to go through this anyway. So last one is again just go through, no problem. I did not read it even. No, I mean you will use it. Do I have to read it? No, no. You read the book. I mean, this is trivial. There is nothing difficult to talk. Yeah, it's just simplifying. One should compare statements A to C of this proposition with the reflexive, symmetric and transitive axioms of equality. It is often useful to think of the notion of epsilon clause as an approximate substitute for that of equality in analysis. So now, first time I guess he brought the word analysis, no? So anyway, after how many chapters? 4 chapters. One more chapter to go. They are also important that these chapters make your brain logical as well as if somebody, you know what you can take for granted and what are the things you need to prove. That's how they are important. Otherwise you may think everything is true. Somebody asks you, why? Oh, it's true, no. Now you after this thing you cannot reply that way. Now we recursively define exponentiation for the natural numbers. I guess time to stop, I think. Enough, because otherwise I will, if I get trapped with the, what? Traffic, I will be in trouble.